Somewhere in the universe right now, a star is dying. Not dramatically, not with an audience. Just quietly collapsing into itself, the way old things sometimes do, pressing inward, gathering, folding the fabric of space around it like a blanket pulled over a sleeping form. You won't hear it. It's too far away and space is too silent, and besides, you are here, warm, breathing slowly, and the universe has all the time in the world. Tonight, we are going to talk about black holes. Not the terrifying kind, the cinematic Hollywood kind with teeth and hunger and dramatic orchestral swells. No, the real kind, the true kind, which are, in their way, so much more extraordinary and so much more peaceful than anything a movie could invent. Black holes are places where the universe reaches its deepest point of stillness, where light itself stops, where time slows down and stretches like taffy until it almost ceases to move at all. They are not evil. They are not waiting for you. They are simply the universe's way of carrying things to their most essential form. So settle in. Let your body get heavy. Let your breathing slow. You don't need to memorize any of this. You don't need to follow along with a pencil or remember what comes next. This is not a lecture. This is a long, quiet walk through one of the most astonishing things the cosmos has ever made. The black hole will wait for us. It has been waiting for millions of years. A few more minutes won't trouble it at all. Let's begin with the simplest possible question, which also happens to be one of the hardest. What is a black hole? The easy answer, the one you might remember from a school textbook, goes something like this. A black hole is a region of space where gravity is so strong that nothing, not matter, not light, not anything can escape. That's true, but it leaves out so much. Think about gravity for a moment. Not the physics classroom version, just gravity as you feel it. The gentle insistence that keeps your body in the chair, keeps the blanket across your chest, keeps the earth beneath your feet. Gravity is the universe's way of saying, things belong together. Mass calls to mass. Every atom in your body is very gently, very quietly, pulling on every atom in the earth beneath you, and the earth is pulling back. Now imagine, just for a moment, that instead of your body, which weighs however many kilograms you weigh, we compress all of that mass. Press it smaller. Press it down into a marble. Now press the marble into a grain of sand. Now press the grain of sand into something smaller than an atom. The gravitational pull doesn't change. There is still exactly as much mass as there was. But now all of that mass is concentrated into an impossibly tiny point. And gravity doesn't spread out anymore, it screams inward. It becomes something else entirely. That is the heart of a black hole. Physicists call it a singularity, a point of infinite density, infinite curvature. A place where the ordinary equations of physics politely raise their hands, say, we don't know what happens here, and sit back down. Around this singularity there is a boundary, a threshold. The event horizon. The event horizon is not a wall. There is nothing physical there to run into. It is simply the point of no return, the line in space past which the escape velocity exceeds the speed of light. And since nothing in the universe travels faster than light, nothing that crosses the event horizon can ever come back. It is the universe's most perfect one-way door. And here is something extraordinary about it. If you were approaching a black hole and you crossed the event horizon, you wouldn't feel a bump. You wouldn't hear a sound. You would simply pass through a kind of invisible membrane. And from that point forward, every possible path you could take, every direction, every choice, every movement would lead deeper in. Inward would become your only future. There are no signs posted at the event horizon, no last warnings, just the universe proceeding with its customary silence. Black holes come in different sizes. And when I say different sizes, I mean it in a way that strains the imagination. At the small end, though nothing about a black hole is truly small, we have stellar mass black holes. These form when very large stars, much larger than our sun, exhaust their fuel and collapse. A star that began its life with perhaps 20 or 30 times the mass of our sun might end its life as a black hole roughly the size of a city, perhaps 20 kilometers across, perhaps 30. Less than the distance between some people's homes and their workplaces, and yet containing as much mass as several suns. Then there are intermediate mass black holes, harder to find, harder to study, but seeming to exist in the hundreds or thousands of solar masses, the middle children of the black hole family. Quieter, less understood. And then there are the supermassive black holes. These are the true monarchs of the universe. Found at the centers of almost every large galaxy, including our own, supermassive black holes contain millions, billions, even tens of billions of times the mass of our sun. The one at the center of our galaxy, which astronomers have named Sagittarius A, contains about 4 million solar masses. The one at the center of the galaxy, M87, which we actually photographed for the first time in 2019, contains about 6.5 billion solar masses, 6.5 billion suns, compressed into a single point, surrounded by an event horizon larger than our entire solar system, and all of it silent, all of it patient, all of it waiting in the dark like a very old and very still thing at the heart of a great wheel of stars. Before a black hole can exist, something else must end. This is one of the universe's quieter truths, that almost everything we consider extraordinary was born from something else's ending. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was scattered across space when a massive sun exploded long before our planet existed. We are made of endings, and black holes are perhaps the most spectacular endings of all. A star lives its entire life in a kind of balance. On one side of the scale, gravity, always pressing inward, always trying to collapse the star into a single point. On the other side of the scale, the outward pressure of nuclear fusion, the process at the star's core that converts hydrogen into helium, releasing energy, generating heat, pushing outward. For millions, sometimes billions of years, these two forces hold each other in check. The star shines. It sits in the sky. It burns with extraordinary patience. But eventually, the fuel runs out. When a small star like our sun runs out of hydrogen, it will expand into a red giant, enormous, cool, and luminous, and then shed its outer layers into a beautiful cloud called a planetary nebula, leaving behind a tiny, dense remnant called a white dwarf. Quiet, cooling, eventually dark, our sun will end that way in about 5 billion years, slowly, gently in cosmic terms. But stars much larger than our sun, stars with 10, 20, 30, 40 or more times its mass, do not go gently. They have spent their lives burning brighter, burning faster, burning through fuel that smaller stars would nurse for billions of years. And when they run out, the collapse is catastrophic. The core, no longer supported by the pressure of fusion, falls inward in less than a second. The speed of this collapse is staggering. The core compresses from the size of Earth down to something roughly 20 kilometers across in less time than it takes you to blink. Then the infalling outer layers of the star slam into this suddenly rigid core and rebound outward in an explosion so violent, so bright, that for a few weeks, a single star can outshine an entire galaxy of hundreds of billions of suns. We call this a supernova. The supernova scatters the outer layers of the star across light years of space, the material that will someday become new stars, new planets, new oceans, new life. And at the center of all that beautiful, expanding debris, something remains. If the remaining core is heavy enough, if enough mass has been compressed into that small, dense remnant, then gravity wins completely. The core continues to collapse, past the point where ordinary matter can resist, past the point where even the weird physics of neutron stars holds firm. and it falls all the way down into something for which the mathematics has no comfortable answer. A singularity. A black hole is born. The whole process, from the beginning of the collapse to the formation of the black hole, takes less than a second. One of the most extraordinary objects in the universe, assembled in less time than it takes to exhale. There is something almost meditative about this. Stars spend millions of years in preparation, burning steadily, transforming themselves through every possible stage of nuclear alchemy. Hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, silicon to iron, each stage shorter than the last, each stage representing a kind of letting go, a deeper surrender to the universe's patient insistence. And then at the end, the final letting go, instantaneous, complete. There are other ways black holes can form too. In the very early universe, when matter was extraordinarily dense and the cosmos was young and hot and turbulent, fluctuations in density may have given rise to what physicists call primordial black holes, objects that formed not from stellar death, but from the sheer compression of matter in the first fractions of a second after the Big Bang. And at the centers of galaxies, the supermassive black holes that now anchor entire systems of hundreds of billions of stars may have grown over billions of years through a combination of merging smaller black holes and consuming enormous quantities of gas and dust. How the very first seeds of these giants formed remains one of the open questions of astrophysics, a mystery written into the darkness at the center of every large galaxy in the observable universe, including our own. Let us take a slow, careful walk around a black hole, not too close. From a comfortable distance, perhaps from the perspective of a spacecraft in a stable orbit, far enough away that the gravitational pull is no more unusual than what keeps the planets circling the sun. From here we would see nothing. That is the first and strangest thing. We would look at the place where we know a black hole exists, and we would see a circular patch of absolute darkness. No light comes from within. No surface reflects our gaze, just an absence, a hole in the visible universe. But around this absence, if we look carefully, the universe would look strange. The light from stars behind the black hole would be bent, curved. The gravity of the black hole acts on light the same way a lens acts on light. It bends paths that would otherwise be straight. Stars that should be hidden directly behind the black hole would appear around its edge, displaced from their true positions, their light stretched into arcs and rings. This effect is called gravitational lensing, and for a black hole, it is particularly dramatic, creating what can appear as a luminous ring of light around the central darkness. The shadow of the black hole surrounded by a halo of bent starlight. This is what the Event Horizon Telescope actually photographed in 2019. Not the black hole itself. You cannot photograph a black hole in the way you photograph a face or a mountain, because there is nothing to reflect the light. What they photographed was this glowing ring, the photon ring, created by light spiraling so close to the event horizon that it nearly fell in, but instead traced a tight loop and escaped to reach our instruments, 55 million light-years away. 55 million light-years. A light-year is the distance light travels in one full year, about 9.5 trillion kilometers, 55 million of those. The light we studied from that black hole left its source before there were humans on Earth, before there were mammals, before there were dinosaurs. When the most complex life on our planet was still mostly single-celled organisms floating in ancient seas. The universe is patient in ways that are genuinely difficult to hold in the mind. Now, let us approach more carefully and learn the parts of this extraordinary structure. At the very center, the innermost point, the deepest deep, is the singularity. Physicists describe it as a point of infinite density and zero volume. All the mass of the black hole, compressed into something that takes up no space whatsoever. In all honesty, we don't really know what the singularity is. The word infinity, appearing in a physical equation, is usually a sign that the equation has broken down, that our model of reality has reached its limits. The singularity is where general relativity, Einstein's theory of gravity, stops being able to describe what's happening. To understand singularities properly, we would need a complete theory of quantum gravity, which unifies general relativity with quantum mechanics. We don't have that theory yet. The singularity may be a point, or it may be that, at the scales where quantum affects matter, it has some structure, some texture, that our current mathematics cannot reveal. It may be that infinite density is not what actually exists there, but rather a symbol of our ignorance, a placeholder for something we haven't yet learned to describe. This is, in its way, comforting. It means the universe still has secrets. The deepest question about the deepest place we know of has not yet been answered. Moving outward from the singularity, we reach the event horizon, that invisible, intangible boundary that defines the edge of the black hole proper, the point of no return. For a simple, non-rotating black hole, the kind described by Karl Schwarzschild's 1916 equations, just weeks after Einstein published his general theory of relativity, the event horizon is a perfect sphere. Its radius is called the Schwarzschild radius, and it depends only on the mass of the black hole. For our sun, if it were compressed into a black hole, the Schwarzschild radius would be about 3 kilometers. For the Earth, it would be about 9 millimeters, roughly the size of a marble. For you, compressed into a black hole, your event horizon would be smaller than a single proton. This gives you a sense of how extraordinarily dense these objects are, and also, perhaps, of how safe you are from becoming one. The universe requires enormous masses and extraordinary circumstances to create a black hole. You are in no danger. Real black holes, however, almost certainly rotate. Stars rotate. Every star we can observe spins on its axis. And when a rotating star collapses, the rotation is preserved and amplified. Spinning black holes are described by a different set of equations, developed in 1963 by Roy Kerr, a New Zealand mathematician. Kerr black holes have not one but 2 event horizons, and their interiors have a structure that is richer and stranger than the Schwarzschild solution. At the center of a Kerr black hole, the singularity is not a point but a ring of infinitely dense matter spinning in space, like a crown made of everything that ever fell in. Just outside the event horizon, there is a region called the photon sphere, a zone where light, if aimed just right, could orbit the black hole indefinitely. Photons, particles of light, could circle around and around in a perfectly balanced orbit, neither escaping nor falling in. In practice, these orbits are unstable. A tiny perturbation, and the photon either spirals in or flies free. But the photon sphere is the boundary of what we can observe, the inner edge of the luminous ring that surrounds the black hole's shadow. In this zone, space itself is so warped that looking backward, you would see the back of your own head. Looking outward, you would see starlight bent into extraordinary patterns, the entire visible universe folded and wrapped around you like the surface of a sphere. All directions, simultaneously containing glimpses of the same distant stars. For rotating black holes, there is a fascinating region just outside the event horizon called the ergosphere. The name comes from the Greek word for work, ergon, because it is possible, in principle, to extract energy from this region. In the ergosphere, space itself is dragged around by the spin of the black hole. This is called frame dragging, and it is a prediction of general relativity, the idea that a massive, spinning object literally pulls the fabric of space-time along with it, like honey being stirred. In the ergosphere, this dragging is so extreme that nothing, not even light, can remain stationary relative to the distant stars. Everything must rotate with the black hole. But you can still escape from the ergosphere if you have enough energy. You haven't crossed the event horizon yet. You're in a strange, twisted region of space-time, but the door out is still open. In 1969, physicist Roger Penrose described a theoretical process by which a spacecraft entering the ergosphere could split in two, letting one half fall in while the other half flew out with more energy than it entered with. The energy comes from the rotational energy of the black hole itself. This is called the Penrose process. No one has built such a spacecraft, but the physics says it would work. Black holes, in the end, are not purely destructive. They are transformative. They take things in and change the universe in the process. Even their deepest regions may eventually, over timescales that dwarf the current age of the universe, give something back. We need to talk about time. Not time as we usually think of it, as a river flowing steadily forward, carrying us from one moment to the next at a constant rate. That picture, as familiar and comfortable as it is not quite true. Einstein showed us, more than a century ago, that time is more flexible than this. That gravity bends time just as surely as it bends space. The more powerful the gravity, the slower time flows. This is not a metaphor. It is not philosophy. It is a measurable, verified everyday fact. The GPS satellites in orbit above our planet must account for the fact that time passes very slightly faster at their altitude, where gravity is slightly weaker, than it does on the surface of the Earth. If the satellites didn't correct for this, GPS would drift out of accuracy within minutes. The engineers who built GPS had to read Einstein carefully, and they did. Now, take this effect and amplify it to the extremes of a black hole. Imagine you have a friend. And this friend, in an act of either great courage or great recklessness, decides to fall toward a black hole while you watch from a safe distance. Your friend falls feet first. You watch through a very good telescope. As your friend approaches the event horizon, something remarkable happens. You watch them slow down. Not because they are physically decelerating, they are actually accelerating, falling faster and faster in terms of the local physics, but because time near the event horizon is running so much more slowly than it runs where you are watching. From your perspective, your friend's fall appears to slow, and slow, and slow. The light reaching you from your friend becomes redder, the wavelength stretching as photons struggle to climb out of the gravity well, and your friend appears frozen, dimming, fading, becoming a ghost of themselves at the edge of the event horizon, stationary, eternal. Your friend never appears to cross the event horizon. From your perspective, they hang there forever, a reddening, fading image, until they become too dim to see. But from your friend's perspective, from inside the fall, nothing unusual is happening at first. Gravity feels, initially, like simple weightlessness. Your friend is in freefall, and freefall feels like floating. Like being an astronaut. The tidal forces, the difference in gravity between the head and the feet, are gentle at first for a large black hole, where the event horizon is far from the singularity. Your friend passes through the event horizon without ceremony, without a bump. There is no wall, no sign, no alarm, just space curving. And now, every path forward leads toward the singularity, not the event horizon behind them, that is no longer behind them in any navigable sense. The singularity is in front of them in the way the future is in front of all of us, unavoidable and approaching at the speed of time itself. This is one of the most disorienting things about black holes. Crossing the event horizon is, in a sense, crossing into a region where the singularity is your future, in the same way that tomorrow is your future. You cannot avoid tomorrow. You cannot navigate away from it. It will arrive. And for your friend inside the black hole, the singularity will arrive. For a supermassive black hole, the enormous kind, billions of times the mass of the Sun. The journey from the event horizon to the singularity could take hours in the experience of the traveler. Time enough to think, time enough to look around at the extraordinary distortion of the universe as seen from inside this region of pure curvature. The light from the outside universe would appear concentrated into a bright circle overhead, growing smaller as the singularity approaches. For a smaller stellar mass black hole, the tidal forces would become lethal long before the singularity. The difference in gravity between head and feet would stretch a human body like taffy in a process that physicists, with characteristic dry humor, call spaghettification. This is not a comfortable way to go, but the supermassive ones, the ancient, enormous ones at the centers of galaxies, those would be more generous with their time. There is also a paradox at the heart of this. You watch your friend freeze at the event horizon, fading forever. Your friend passes through the event horizon and continues falling. From the outside, they are frozen. From the inside, they are moving. Both perspectives are valid, both are real. They are simply two different experiences of the same geometry, two different views of the same warped spacetime. The universe does not insist on a single version of reality. It allows many. It is possible, lying here in the dark, to feel something like peace about this, about time being flexible, about the present moment being, in a deep sense, a matter of perspective. Your night lying here, moving slowly towards sleep, is not identical to any other moment in the universe. Your time is your own. And it is passing at exactly the rate that feels right here in this quiet. Black holes eat, not actively, not with hunger in the way we think of hunger. But matter falls in, drawn by gravity, and black holes grow. And the process of this feeding, of matter spiraling down toward the event horizon, is one of the most energetic and luminous processes in the observable universe. When a black hole is actively consuming matter, when gas and dust and occasionally entire stars are spiraling inward, the material doesn't fall straight in. It falls in a spiral, a disk. The same way water spirals down a drain, or the way debris accumulates in orbit around a planet. Orbiting matter tends to form a flat, spinning disk because all the different infall trajectories average out to something flat. This disk, called an accretion disk, is not quiet. The gas within it is moving at tremendous speeds, different layers moving at different rates, and the friction between these layers heats the gas to extraordinary temperatures. Millions of degrees, tens of millions of degrees, hot enough that the accretion disk glows not in ordinary visible light, but in X-rays. Active black holes with large accretion disks are among the brightest objects in the universe. We call them quasars, or active galactic nuclei, depending on the context. The luminosity of a large quasar can be thousands of times brighter than the entire Milky Way, hundreds of billions of suns worth of energy, generated not by the nuclear fusion of stars, but by the sheer violence of matter falling toward a point. And here is one of the quiet ironies of black holes. The most luminous objects in the universe are powered by the same process that creates the darkest objects in the universe. The brilliant quasar and the silent, invisible black hole are the same thing, one being actively fed, one resting in the dark. Our own galaxy's central black hole, Sagittarius A, is currently quiet. It is not consuming very much material. It sits at the center of the Milky Way like an ember, still there, still extraordinarily massive, but no longer burning with the ferocious brightness of its youth. Long ago, when the Milky Way was young and rich with gas, Sagittarius A was almost certainly an active quasar. It blazed. It may have been visible were there eyes to see it across the entire galaxy. Now it rests. In 2022, astronomers captured the first actual image of Sagittarius A glowing ring of orange-gold light around a central darkness. taken by the Event Horizon Telescope collaboration, the same group that had imaged M87's black hole 3 years earlier. There it was, 4 million solar masses, 26,000 light-years from where you are lying right now, the quiet anchor of our galaxy, ordinary, ancient. There, stars also fall into black holes. Not often, but it happens. A star that wanders too close to a supermassive black hole in the center of its galaxy can be disrupted by tidal forces, torn apart, its material stretched into long streamers that spiral inward. This is called a tidal disruption event, and for a few weeks or months it creates a brilliant flare of energy. A last bright moment before the star's material joins the accretion disk and eventually crosses the event horizon. We have observed dozens of these events. There is something almost elegiac about them. A star that spent billions of years shining faithfully, contributing its light to its galaxy, meeting its end in a few months of extraordinary brightness, before finally, quietly disappearing. Everything ends, but some endings are beautiful. Black holes give as well as take. Not everything that falls toward a black hole actually falls in. The magnetic fields in an accretion disk are twisted and concentrated by the swirling plasma, and they can launch some of the infalling material outward, not inward, but outward in two narrow beams perpendicular to the disk. Jets, relativistic jets, these jets are extraordinary. Material shot outward at close to the speed of light, 90, 95, 99% of the speed of light, in tight columns that can stretch for hundreds of thousands of light years. For context, our entire Milky Way galaxy is about 100,000 light years across. The jets from some supermassive black holes extend farther than the diameter of our galaxy. They carry energy out into intergalactic space. They heat the diffuse gas between galaxies. They regulate the rate at which galaxies form new stars, acting as a kind of thermostat. When the gas gets too cool and begins collapsing into stars too rapidly, the jet heats it up and slows the process down. Black holes in this way are not passive, they are architects. The large-scale structure of the universe, the arrangement of galaxies into filaments and sheets and voids, was shaped in part by the feedback of supermassive black holes on their surrounding environments. The rate of star formation across the history of the cosmos, the distribution of metals throughout intergalactic space, the temperatures of galaxy clusters. All of these bear the fingerprint of black holes at their centers. We live in a universe that has been sculpted by its darkest objects. The Milky Way itself was shaped this way. The current quiet of Sagittarius A, the emptiness of the region immediately surrounding it, the particular distribution of stars and gas in our galaxy's central bulge. All of this reflects the history of our own central black hole. Billions of years of activity and feeding, and the eventual quieting down into the current stillness. Every galaxy, in a sense, is a monument to its central black hole. The spiral arms, the older stars, the chemistry of the nebulae where new stars form, all of it bears the imprint of that massive, ancient, central engine. And we are part of that monument, made from the gas that circulated in our galaxy's early history, marked by the chemistry that billions of years of stellar birth and death have laid down. The universe, working through black holes, helped write the conditions that eventually allowed us to exist and to lie here in the dark and wonder about it. There is one more thing you should know about black holes before we continue our journey deeper into the night. Black holes evaporate, not quickly, not in any way that is observable with current technology for any black hole that exists in the universe today. But over time, extraordinary spans of time, they do. This was the insight of Stephen Hawking, published in 1974. Using a combination of quantum mechanics and general relativity, two theories that are, in most circumstances, deeply incompatible. Hawking showed that black holes should emit thermal radiation from just outside their event horizons. The mechanism is subtle and strange. In quantum mechanics, the vacuum of space is not truly empty. It is a sea of fluctuating energy, where pairs of virtual particles, a particle and its antiparticle, constantly pop into existence for the briefest moment and then annihilate each other, returning their borrowed energy to the vacuum. This happens everywhere always. Near the event horizon of a black hole, something unusual can happen. One particle of a virtual pair falls across the event horizon before the pair can annihilate. The other particle escapes. To conserve energy, the black hole must pay the energy debt of the escaping particle, which means the black hole loses a tiny amount of mass. And the escaping particle becomes a real particle, carrying real energy away from the black hole. This is Hawking radiation. It is fantastically, almost inconceivably slow for any black hole of stellar mass or larger. The temperature of the radiation from a stellar mass black hole is roughly 10 millionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole is actually absorbing more energy from the CMB than it emits in Hawking radiation, meaning it is growing, not shrinking. For a black hole to actually evaporate, to lose mass faster through Hawking radiation than it gains it from the universe around it, the universe would first need to cool below the Hawking temperature of that black hole. And the universe is still far too warm for any black hole we know of. But the universe is expanding, and as it expands, it cools. And in a very, very distant future, we are talking about timescales with so many zeros that writing them out requires scientific notation, and even then the numbers barely communicate their magnitude, the cosmic. Background radiation will have cooled enough that large black holes will begin, ever so slightly, to lose mass. For a black hole of about 1 solar mass, the evaporation time is roughly 2 times 10 to the power of 67 years. That is a 2 followed by 67 zeros. For comparison, the current age of the universe is roughly 14 billion years, about 1.4 times 10 to the power of 10. The numbers are not comparable in any meaningful human sense. One is an afternoon. The other is the distance to the horizon of everything. For a supermassive black hole of 1 billion solar masses, the evaporation time is proportionally longer, so long that it makes the stellar mass black hole's timeline look brief. But here is what is quietly, almost spiritually remarkable. It happens. Even black holes, the densest, most implacable structures the universe has produced, are not eternal. Even they surrender, eventually. Even they dissolve back into the quantum vacuum from which everything came and to which everything returns, in the very final moments of evaporation. As the black hole shrinks and its Hawking temperature rises, because smaller black holes are hotter in Hawking radiation terms, it emits a final burst of radiation and disappears. Not with a catastrophic explosion of ordinary matter, just a last pulse of energy, and then nothing. The information problem, whether the information about everything that ever fell in is somehow encoded in the Hawking radiation, remains one of the deepest open questions in all of physics. Hawking himself spent decades wrestling with it, changing his position, publishing papers, arguing with colleagues across the decades of his working life. The question is not settled. The universe keeps its deepest secrets behind the very horizon that makes them inaccessible. On April 10th, 2019, human beings saw a black hole for the first time, not with any single telescope. No single instrument on Earth or in space could have made this image. It required a collaboration, the Event Horizon Telescope project, that turned the entire surface of the Earth into a single, planet-sized telescope. The The trick in radio astronomy is called very long baseline interferometry. Two radio telescopes on opposite sides of the planet can be synchronized so precisely that the data they collect can be combined. And the result is equivalent to a single telescope with a dish as wide as the distance between them. Wider dishes collect more light and produce sharper images. The Event Horizon Telescope linked 8 radio observatories around the world. In Hawaii, in Arizona, in Spain, in Mexico, in Chile, in Antarctica, and Greenland. Together, they formed a virtual telescope with the diameter of our entire planet. And they all pointed simultaneously for several days at the center of the galaxy M87. Pause. The data came in. Petabytes of it, so much that it had to be physically shipped on hard drives because no internet connection was fast enough to transfer it. The data from the South Pole telescope had to wait for the Antarctic winter to end before it could even be shipped. Scientists waited 6 months before they had all the pieces. Then, the analysis. The reconstruction of the image from the data required new algorithms, new mathematics, months of computation. 4 independent teams worked on the reconstruction separately so that no single team's assumptions could bias the result. They compared their images, and they matched. A fuzzy, glowing ring of orange gold light around a patch of pure darkness. The shadow of a black hole, 6.5 billion times the mass of our sun. An event horizon larger than our entire solar system, 55 million light years away. When the image was published, it went everywhere almost instantly. People who had never thought about black holes before looked at this small, blurry circle of light and understood, perhaps for the first time, what it meant. There is a place in the universe where space itself curves completely closed. And we found it, we looked at it, and now we can say that is real, that is there, that is what it looks like. 3 years later, in 2022, the same collaboration published the first image of Sagittarius A, the black hole at the center of our own galaxy. This one was harder. Despite being much closer than M87's black hole, 26,000 light-years versus 55 million, it is also much smaller. And the matter around it moves so quickly that the appearance of the accretion region changes on the timescale of the observations. The team had to develop special techniques to account for this, but there it was, the same glowing ring, the same shadow, our galaxy's own anchor seen for the first time. Something that has been at the center of the Milky Way since before our sun existed, that shaped the distribution of billions of stars. That blazed as a quasar in the ancient universe, and then quieted into its current meditative stillness. And now we have its portrait. There is something deeply moving about this. Not just the science, the extraordinary technical achievement, the ingenuity, the patience, but the simple fact of looking. The human impulse to understand, to turn toward the darkest, most unreachable thing and say, "Tell me what you are." The black hole, of course, does not answer in words. It answers in light, bent, reddened, struggling, beautiful, curved around the event horizon and sent across millions of light years to fall on our instruments and become, at last, visible. We have walked around the outside. We have studied its anatomy, its history, its light. Now let us imagine something we can never do. Let us imagine going in. Not the violent, destructive version, not the spaghettification, not the tidal forces. Let us imagine the gentlest possible version. A traveler in a well-shielded spacecraft, approaching the supermassive black hole at the center of a distant galaxy. Something in the range of 10 billion solar masses. Something large enough that the event horizon is far enough from the singularity that the tidal forces at the horizon are, at first, survivable. Pause, breathe. From far away, the approach is unremarkable. Stars shine normally. The spacecraft is in freefall, weightless, peaceful, drifting on a long arc toward the center. Instruments confirm that the black hole is there, Its mass bends the paths of nearby stars, and occasional accretion activity produces brief flickerings of X-ray emission. But to the eye, there is simply a dark region ahead, surrounded by the bent and brightened light of stars behind it. As the spacecraft draws closer, the gravitational lensing becomes more dramatic. Stars near the edge of the black hole's shadow are displaced from their expected positions, their light bent around the curve of spacetime. Looking in any direction near the black hole's silhouette, the traveler would see distorted, curved starfields, the familiar constellations warped beyond recognition. The entire visible universe arranged into a ring at a specific angle of vision. This ring, the Einstein ring, grows larger and more complex as the spacecraft approaches. Secondary images of bright stars appear, light that has traveled once around the black hole before reaching the observer. Then tertiary images, light that has looped twice. The universe from this vantage is kaleidoscopic. Infinite copies of the same stars arranged in concentric rings, each slightly dimmer, each representing light that has looped the black hole one more time than the ring outside it. The event horizon is crossed without ceremony. There is no bump, no sound, no physical sensation of anything unusual. The clocks on board are still running, the instruments are still reading. The traveler is alive and unharmed, but the universe outside has changed. The ring of light from the outside universe, which was once an equatorial band seen at 90 degrees from the direction of the black hole, has now shifted. It is above the spacecraft now. It is narrowing. The visible outside universe is condensing into a smaller and smaller circle of light overhead. Everything behind is dark. Everything ahead is dark. Only this shrinking circle of starlight above. All the light from all the galaxies and stars outside the black hole, compressed into a disk that grows smaller as the singularity approaches. The traveler looks up at this compressed universe, this entire observable cosmos, visible stars and distant galaxies, and the glow of the cosmic microwave background, all packed into a narrowing circle, and sees something no human has ever seen or will ever see. The universe from the inside of a black hole. Time is still passing, but the clock is running down. The singularity is in the future now, unavoidably, inexorably in the future. The way death is in every living creature's future, not threatening every moment but there, at the end of the road. Patient, what the singularity is at the end, is beyond current physics. Whether the classical description breaks down, whether quantum effects change the structure before the traveler arrives, whether information is somehow preserved in ways we cannot yet describe, these are open questions. The singularity remains the universe's deepest held secret. But the journey there, the long, weightless, extraordinary fall, is something that the mathematics of general relativity describes in beautiful, elaborate detail. The geometry of the fall, the distortions of light and time, the narrowing circle of the universe overhead, the perfect, terrible quietude of it all. A black hole is, among other things, the most solitary place in the universe. Once inside, no signal can reach the outside, no message can be sent, no story can be told. The traveler and everything they experience is contained, sealed, and in some interpretations of black hole physics, the traveler, from their own perspective, simply continues. The singularity ends their classical trajectory, but the quantum information of their existence is preserved, somehow, in the radiation emitted by the black hole over the timescales of its evaporation, scrambled, unreadable but not destroyed. Return to the universe, eventually in the form of Hawking radiation, long after the black hole itself is gone. We are made of stardust. Everything that has ever fallen into a black hole may, in the very longest possible run, become something again, changed beyond recognition. But there, let us come back closer to home for a while. At the center of our galaxy, the Milky Way, the galaxy in which our sun and all its planets and all the life we know of resides, there is a black hole called Sagittarius A. The asterisk in its name is an astronomical convention for certain kinds of radio sources. Astronomers are sometimes charmingly literal. The star in the name is simply a designation. But there is something poetic about it regardless. The heart of our galaxy bearing a small star in its name. Pause. Breathe slowly. Sagittarius A is 4 million times the mass of our sun. Its event horizon is roughly 24 million kilometers across, about 17 times the diameter of the sun. This sounds enormous, and it is, but on the scale of the galaxy it is tiny, a marble at the center of a city. It lies about 26,000 light-years from our solar system. This is close in galactic terms. Our sun is roughly halfway out from the center of the Milky Way. In one of its spiral arms, the Orion Arm, and from our position, we are well within the gravitational influence of the galaxy as a whole, orbiting the center just as the planets orbit the sun. Our sun takes about 225 million years to complete one orbit around the galactic center. This is sometimes called a galactic year, or a cosmic year. In the history of our solar system, roughly 4.5 billion years old, we have completed about 20 galactic orbits. We have been around the block 20 times. Sagittarius A has been at the center the entire time. For most of the history of science, we knew the galactic center was there. We could see the dense clustering of stars and gas clouds in the direction of the constellation Sagittarius, but we could not see through all the dust and gas between us to examine it directly. Visible light cannot penetrate the interstellar medium between us and the center. Radio waves can, infrared light can, X-rays can. And as we developed instruments sensitive to these wavelengths, the galactic center gradually revealed itself. The most compelling early evidence for a black hole at the galactic center came from observations of stars orbiting close to Sagittarius A. Stars so close that they complete full orbits in just years, not millions of years like our sun's galactic orbit, but actual years, short enough for astronomers to watch the orbits change. From these orbits, the mass of the central object could be calculated with extraordinary precision. One star, designated S2, has a highly elliptical orbit that brings it within about 17 light-hours of Sagittarius A at its closest approach. At this distance, it travels at nearly 3% of the speed of light. Astronomers have tracked S2 for multiple complete orbits, and the data reveals both the mass of the central object and, through the subtle distortions predicted by general relativity, the fact that this mass is indeed a black hole and not any other kind of dense object. Watching S2 orbit Sagittarius A is, in miniature, like watching the moon orbit the Earth, except that what S2 is orbiting is 4 million solar masses compressed to a diameter smaller than our planetary system. And every aspect of S2's motion bears the fingerprint of the most extreme gravitational environment in our galactic neighborhood. Sagittarius A is currently quiet. It eats very little. Occasionally there are X-ray flares, brief brightenings lasting an hour or so. That may represent small clouds of gas or asteroids being tidally disrupted near the event horizon. But by the standards of active galactic nuclei, it is almost completely dormant. This is unusual for a black hole of its mass. Many galaxies comparable to the Milky Way host more active central black holes. Ours appears to have settled into an unusual quietude. Perhaps it consumed most of the available fuel long ago. Perhaps the geometry of the Milky Way's center limits the supply of infalling material. The reasons are not fully understood. What is clear is that we live in a galaxy whose central engine has largely switched off, and that this quietude may be part of why the Milky Way is the kind of place where stable planetary systems can exist and life can arise and ponder its origins. A more active galactic center might periodically flood the galaxy with radiation energetic enough to disrupt the chemistry of planetary atmospheres, or destabilize planetary systems through gravitational perturbations. Our quiet black hole may be, in an indirect and impersonal way, a condition for our existence. Even the darkness at the heart of things can be a kind of gift. When two black holes find each other, the universe takes notice, not in any way we can see. Black holes, by their nature, emit no light. Two black holes spiraling toward each other in the emptiness of space are invisible, but they are not silent, not to the right kind of instrument. They speak in gravitational waves. Gravitational waves are ripples in the fabric of spacetime itself, distortions in the geometry of space and time that travel outward from their source at the speed of light. Einstein predicted them in 1916 as a consequence of his general theory of relativity. But for nearly a century, no one could detect them. The waves are real, but they are extraordinarily faint. The stretching and squeezing of space that a gravitational wave produces, even from violent cosmic-scale events, is, by the time it reaches Earth, smaller than a proton. To detect something that small requires the most sensitive measurement instruments ever built. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses lasers and mirrors arranged in L-shaped arms 4 kilometers long. The lasers bounce back and forth along these arms, and a gravitational wave passing through the Earth stretches one arm and compresses the other by an infinitesimal amount. The instrument is sensitive enough to detect a change of less than 1,000th the diameter of a proton. On September 14, 2015, LIGO detected its first gravitational wave. The signal lasted less than a quarter of a second. But in that fraction of a second, encoded in the subtle chirp of the wave's frequency and amplitude, was the story of two black holes, one about 36 solar masses, one about 29 solar masses, that had been spiraling toward each other for perhaps 1 billion years, and in their final moments, orbited each other hundreds of times per second, closer and closer, until they merged into a single black hole of about 62 solar masses. 3 solar masses of energy were radiated away as gravitational waves in that final fraction of a second. More energy than all the stars in the observable universe combined emit in light during that same interval. 3 solar masses, just gone, converted directly to gravitational radiation and sent rippling across the universe. And one of those ripples reached Earth 1 billion years later and made 2 4-kilometer tubes stretch and compress by a distance smaller than an atomic nucleus. And we heard it. Since that first detection, LIGO and its partner detectors, Virgo in Europe, KAGRA in Japan, have detected dozens of merger events. Black holes meeting black holes, neutron stars meeting neutron stars, black holes meeting neutron stars. Each event is a brief, faint whisper in the geometry of space, a message that traveled for millions or billions of years to arrive at exactly this moment, this place, this set of instruments. We have, for the first time in history, developed the ability to hear the universe. Not through sound, space is silent in the conventional sense, but through the warping of spacetime itself. Gravitational wave astronomy is a new sense, a way of perceiving the cosmos through a channel that had been there since the universe began, accessible to anyone who built the right instrument and listened. What is extraordinary is not just the science, it is the patience. Scientists worked for decades to build LIGO. Earlier iterations of the detector were not sensitive enough. They upgraded, rebuilt, improved. They believed the signal was there. They listened and kept listening for years before they heard anything. And then on a Tuesday morning in September, the universe finally spoke. In the data, the gravitational wave signal from two merging black holes sounds, when converted to audio frequencies, like a chirp. A rising note, a brief glissando, ending in a single low thump as the merger completes. It lasts a fraction of a second. In that fraction of a second is encoded an entire relationship, the slow inspiral across a billion years, the final violent dance, the union into a single object. The ringdom as the new black hole settles into its final configuration. The universe compresses a billion years into a chirp. We compress it further into a sound file of less than a second. And in that sound file is the most intimate portrait we have of two black holes meeting. Here is one of the deepest questions in modern physics, stated as simply as possible. If you throw a book into a black hole, does the information in the book survive? Not the physical paper, not the ink. Those are destroyed, torn apart by tidal forces, scattered by the accretion disk, eventually converted to energy and consumed by the singularity. But the information, the arrangement of letters, the particular patterns of words, everything that made that book rather than any other object, does that survive? In ordinary physics, the answer is, information is conserved. Physics is reversible. Given the current state of any isolated system, you can, in principle, calculate its past and future states. Nothing is ever truly lost. A book burned to ash retains, in the arrangement of the ash and smoke and heat, every piece of information needed to reconstruct the book, if you could only measure everything precisely enough. Information is preserved, but a black hole seems to violate this. If matter falls across the event horizon and the black hole eventually evaporates entirely through Hawking radiation, the Hawking radiation is, according to Hawking's original calculations, thermal. Random, it carries no information about what fell in. The particular configuration of atoms in that book is simply gone, not transformed, not encoded somewhere else, gone. This is the black hole information paradox, and it has occupied the minds of the world's greatest physicists for 50 years. Some said, Hawking's original calculation must be wrong. The Hawking radiation is not truly random. At a quantum level, it must carry subtle correlations that encode the information of everything that fell in. The radiation looks thermal if you look at any individual particle, but the correlations between particles, taken all together, reconstruct the information. We just don't know how yet. Hawking himself in his later years came to believe this. That information is preserved, encoded in the correlations of Hawking radiation, but the mechanism remains unknown. Others took a more radical position. Maybe information really is destroyed. Maybe black holes are a genuine exception to the conservation of information, and we need to revise our understanding of quantum mechanics to accommodate this. This view is now largely out of favor, but it has not been definitively ruled out. More recently, a beautiful and strange idea has gained traction: the holographic principle. The idea that all the information about a three-dimensional volume can be encoded on the two-dimensional surface surrounding it. In this view, All the information about everything that falls into a black hole is encoded on the event horizon, on the two-dimensional boundary, not in the three-dimensional interior. The event horizon is like a hologram of everything within it. If this is correct, and many physicists believe it is, though the details remain incomplete, then the black hole doesn't destroy information. It stores it in a scrambled, encrypted form on its surface. And as the black hole evaporates, this information is slowly, painstakingly returned to the universe through the correlations in Hawking radiation. The book thrown into the black hole is not gone. It is written on the event horizon, invisible and unreadable from the outside, mixed into the structure of space at the edge of the point of no return. And over the timescales of the black hole's evaporation, those unimaginable spans of time we discussed earlier, every last bit of its information is returned, transformed to the universe. Nothing is ever truly lost. The universe forgets nothing. It may scramble, may encrypt, may transform beyond any hope of reading, but it keeps every page of every book. There is something quietly reassuring about this, even if the physics is uncertain. The universe has a memory. Even in the darkest, most consuming places it has created, something is preserved. Let us travel for a while. Let us visit some of the most extraordinary black holes we know of, spread across the observable universe. This is a slow journey, no need to rush. The distances are incomprehensible in human terms, but that is part of the beauty. In the constellation Cygnus, about 6,000 light-years from Earth, a stellar mass black hole orbits a blue supergiant star called HDE 226,868. The two objects orbit each other every 5.5 days, so close that the black hole draws material from the outer layers of its companion star, forming a bright accretion disk that makes the system one of the strongest X-ray sources in the sky. Cygnus X1 was, for many years, one of the best candidates for the first confirmed black hole. Stephen Hawking had a friendly bet with physicist Kip Thorne about whether it was a black hole or something else. In 1990, Hawking conceded the bet. The evidence was overwhelming. Cygnus X1 is a black hole. It contains roughly 21 times the mass of our Sun. It was identified in 1964 by a rocket experiment, one of the first X-ray sources ever detected from space. We have been studying it for over 60 years now. And still, every X-ray telescope launched looks towards Cygnus and finds it there, faithfully glowing in high-energy light, consuming a little more of its companion with every orbit. About 36,000 light-years away in the constellation Aquila, a black hole called GRS 1915+105 is one of the most active and variable X-ray binaries known. It contains about 12 solar masses and is locked in an orbit with a red giant companion. It is sometimes called a microquasar. In miniature, it replicates some of the behavior of the supermassive black holes at the centers of active galaxies, including launching relativistic jets. The jets from GRS 1915+105 were among the first ever imaged moving at apparent speeds exceeding the speed of light, an illusion called superluminal motion, caused by the jet moving very close to the speed of light almost directly toward us, so that successive pulses of emission arrive in rapid succession, creating the illusion of faster-than-light travel. The physics is mundane. The appearance is extraordinary. At the edge of the observable universe, over 10 billion light-years away, there is a quasar whose central black hole contains approximately 66 billion solar masses. 66 billion. Ton 618 is one of the most massive black holes ever measured. Its event horizon is so large that if you placed it at the center of our solar system, it would extend well beyond the orbit of Neptune, past Pluto, into the outer reaches of the Kuiper Belt. The entire region of space that we think of as our planetary system would fit inside it. The quasar itself, the blazing accretion disk around this monster, is producing light equivalent to about 140 trillion suns. In the brief span of cosmic time during which it was active, it consumed unimaginable quantities of gas. What it looks like today, we cannot know. The light we see left Ton 618 more than 10 billion years ago, when the universe was only a few billion years old. What exists at those coordinates today is a mystery. A galaxy, certainly, surrounding the remnant of that extraordinary engine. But how active it still is, how much the black hole has continued to grow, we will not know for another 10 billion years, when the light from that era finally reaches us. In 2018, astronomers reported measuring a black hole in the brightest galaxy of the galaxy cluster Abell 85, about 700 million light-years away. Their measurement suggested a mass of about 40 billion solar masses, possibly the most massive black hole ever directly measured. The galaxy containing it, NGC 1277, is an unusual compact elliptical galaxy whose central black hole is so massive relative to the size of the galaxy itself that it constitutes a substantial fraction of the galaxy's total mass. Normally, black holes are a tiny fraction of their host galaxy's mass. This one is anomalous, perhaps the remnant of a larger galaxy that was stripped of its outer stars, leaving the central black hole disproportionately prominent. The universe contains surprises. Every time we think we understand the range of what is possible, something extraordinary turns up in the data. Black holes have been part of the human imagination for longer than we have had the mathematics to describe them. The idea that something might fall into darkness and not return, that there might be regions of existence from which escape is impossible, is ancient. It appears in mythology and religion in the stories cultures tell about death and the underworld, Hades, Sheol, the void, the abyss. These are not black holes in the physical sense, but they represent the same intuition, that the universe contains irreversible passages, doors that open only one way. The physicist John Michell, in 1783, was perhaps the first to reason quantitatively about what we now call black holes. Using Newtonian mechanics, not yet Einstein's relativity, he calculated that an object massive and dense enough would have an escape velocity exceeding the speed of light, and light emitted from its surface would be unable to escape. He called these dark stars. His paper was largely forgotten for nearly 2 centuries. Pierre-Simon Laplace reached similar conclusions independently in 1796. 2 scientists, working separately in a world before photography, before radio, before electricity, before any instrument capable of detecting the universe, beyond what the naked eye could see, reasoning from pure mathematics and Newton's gravity to the conclusion that the universe might contain invisible objects of extreme density, objects that 2 centuries later we would confirm are real. The name black hole itself is surprisingly recent. It was popularized by the physicist John Archibald Wheeler in 1967, though it had been used occasionally before Wheeler's adoption of the term. These objects were called gravitationally collapsed objects, or frozen stars, or Schwarzschild singularities. Wheeler understood that science needs evocative language, and black hole was instantly, memorably precise. It described exactly what it was, a hole in space, and it was black. In popular culture, black holes have often been portrayed as threats, cosmic vacuums, monsters waiting to swallow spacecraft and unwary travelers. In the film Interstellar, released in 2014, the black hole Gargantua was depicted with unusual scientific accuracy. The visual effects team worked with physicist Kip Thorne to simulate what a black hole's gravitational lensing would actually look like. The result was stunning and strange, and unlike any previous cinematic black hole, the disk glittering around the equator, the lensed reflection of the upper disk visible above the shadow, the deep silence of the event horizon. It looked like mathematics. Thorne later wrote that the visual effects work actually produced new scientific insights. The computer simulations required to render the images led to discoveries about what highly warped gravitational lensing looks like, which had not previously been worked out in detail. Art and science finding each other again, the way they always do eventually. There is also a tradition of using black holes as metaphors for human experience. Depression, grief, the feeling of being trapped in something from which there is no escape. These metaphors are powerful precisely because black holes are real. They are not just imaginative constructs. When someone describes the pull of despair as gravitational, as something that bends all paths inward, that makes escape seem geometrically impossible. They are reaching for something true about the physics of the darkest things we know of. And the physics offers a response. Even black holes evaporate. Given enough time, incomprehensible time, it is true, even the most implacable gravity releases what it has held. Nothing lasts forever, not even the event horizon. Most black holes, most of the time, are doing very little. They are not consuming stars. They are not blazing as quasars. They are simply sitting in the darkness, their mass exactly as it was the day they formed, curving the spacetime around them with perfect, patient geometry. Stellar mass black holes drift between stars, invisible, occasionally perturbing the orbits of nearby objects, but otherwise undetectable. Supermassive black holes sit at the centers of galaxies, spinning slowly, waiting. There is something deeply contemplative about this image, the black hole as a meditating form. All its potential held perfectly still. No output, no activity, just being what it is with complete, undistracted consistency. We have discovered some of these quiet black holes only by accident, by noticing the subtle gravitational influence on nearby stars, or by catching the brief flare of a tidal disruption event, when an unlucky star wandered too close. Most dormant black holes will never be individually discovered. They will persist in the dark, drifting through the galaxy, until the galaxy itself disperses over incomprehensible timescales. Some calculations suggest there may be 100 million stellar mass black holes in the Milky Way alone, 100 million of them, invisible, silent, scattered through the galaxy like seeds. The galaxy we see, the spiral arms, the nebulae, the star clusters, is only part of the Milky Way. There is another Milky Way, invisible, made of these dark remnants, permeating the visible one. When we look up at the night sky and see the band of the Milky Way stretched overhead, and you should see it someday from a truly dark location, the way it fills the sky with a soft, luminous river of stars, we are seeing the visible part of a much larger, much darker structure. The part that shines is a minority. Most of the galaxy is dark matter of various kinds, stellar remnants, black holes, the dark between the stars. We live in the luminous fraction of a much larger darkness. This is not a bleak observation. It is, if anything, the opposite. The darkness is not empty. It is full of things that simply do not shine. Things that are real and massive and complex, that exert gravitational influence, that will outlast every star in the galaxy. The part that shines is temporary. The dark parts persist. In a very long time, after all the stars have burned out, after all the white dwarfs have cooled to black dwarfs, after all the neutron stars have slowly radiated their heat away, the last permanent residents of the galaxy will be the black holes. They will be the universe's final anchors, orbiting each other in increasingly decayed, eccentric paths, slowly losing energy to gravitational wave emission, spiraling inward over timescales that make the current age of the universe seem like a morning. Eventually, they will merge. And then the merged black holes will orbit other black holes and merge again, until all the mass of the galaxy has been gathered into a single, enormous black hole, the last remnant of everything that was. And then, over the truly deep time of Hawking evaporation, even that will slowly release itself back into the thermal hum of the universe. This is the deepest fate of our galaxy, of all galaxies. The universe, in the very long run, belongs to the void. We have been talking about black holes as they are understood and observed. But black holes also live at the edge of where physics reaches into pure speculation, and it would be dishonest not to acknowledge that edge. The mathematics of general relativity permits solutions that connect two separate regions of spacetime through a kind of tunnel. Einstein himself, working with Nathan Rosen in 1935, described what is now called an Einstein-Rosen bridge, a mathematical connection between two black holes that could, in principle, link distant regions of the universe. We call these wormholes. The honest statement about wormholes is, the mathematics allows them. We have no observational evidence for them. And the conditions required for a traversable wormhole, one through which matter could actually travel, likely require exotic forms of matter with negative energy density that may or may not exist in our universe. But the imagination finds them irresistible. A tunnel through which you could step from here to a distant star, or from now to another time. A shortcut through a universe that is otherwise far too large to cross. A door at the bottom of a black hole that opens somewhere else. Whether this is physics or poetry, we cannot yet say. The universe has surprised us before. Things that seemed purely mathematical, gravitational waves, black holes themselves, turned out to be real and detectable. Perhaps wormholes are in that category. Perhaps they are a mathematical curiosity with no physical realization. We genuinely do not know. What we do know is that black holes exist at the boundary of what we understand. And at that boundary, the line between the known and the imagined becomes thin. The mathematics of spacetime is strange enough that the imagination is not an unreliable guide. It is, at minimum, a useful companion on the journey toward the next theory, the next framework, the next understanding that will make today's questions look as quaint as Laplace's dark stars. Look to the physicists who confirmed Schwarzschild's calculations. The universe invites wonder, and black holes at the edge of everything we know are one of the places where wonder is most at home. Let us take a moment near the end of our journey to sit with some numbers, not to analyze them or to test on them, just to feel them. To let the scale wash over you the way the sound of rain washes over you, not understood exactly, but felt. The nearest stellar mass black hole we know of is in a binary system called A6200, about 3,000 light-years from Earth. 3,000 light-years. Light takes 3,000 years to make that journey. The Milky Way galaxy is about 100,000 light-years across, so this black hole is relatively nearby, a neighbor, in galactic terms. The supermassive black hole at the center of our galaxy, Sagittarius A, is 26,000 light-years away. The light we use to study it left before modern humans existed, before agriculture, before writing, before any civilization. It has been traveling toward us since the last ice age. The black hole at the center of M87, which we photographed in 2019, is 55 million light-years away. The light left during the Eocene epoch on Earth, when early mammals were diversifying after the extinction of the dinosaurs, when there were no grasses, no whales, no elephants, when the world was warm and humid and full of strange, unfamiliar creatures. Ton 618, that extraordinary supermassive quasar, is over 10 billion light-years away. The light left when the universe was less than 4 billion years old, before our sun existed, before the Milky Way had fully formed. When the universe was young and blazing with quasars and star formation in its most intense phase. The farthest black holes we can detect are near the edge of the observable universe, roughly 46 billion light-years from Earth in the current moving distance, though the light we receive from them has been traveling since a much shorter time after the Big Bang. The observable universe has a radius of about 46 billion light-years. Beyond that edge, the universe continues, likely forever, but the light from those regions hasn't had time to reach us since the universe began. And in all that observable volume, a sphere 46 billion light-years in radius, almost every galaxy we know of contains a supermassive black hole at its center. There are roughly 2 trillion galaxies in the observable universe, 2 trillion, with one central black hole each, plus all the stellar mass black holes scattered through each of those galaxies. Perhaps 100 million per galaxy. The universe is, in some sense, mostly black holes. We live on a small planet around a medium-sized star in the outer suburbs of a reasonably average galaxy, in a universe full of the darkest objects imaginable. And somehow we have found ways to see them, to measure them, to take their portraits, to feel their voices through the instruments of our own making. Somehow we are here, and somehow we are paying attention. We have traveled a long way tonight. From the quiet collapse of massive stars, to the anatomy of event horizons, to the slow dance of gravitational waves rippling through space-time. From the first blurry photograph of a black hole's shadow, to the imagined interior of the largest black holes in the universe. From the deep time of Hawking evaporation to the deep scale of 2 trillion galaxies, each with a dark anchor at its center. And now we come back to Earth, back to this room, back to the warmth under this blanket and the particular quality of this darkness, which is not the darkness of a black hole but the ordinary, friendly darkness of night, made not of collapsed space-time but of the slow rotation of our planet, turning its face away from the sun for a few hours. Our darkness is temporary. The sun is still there on the other side of the planet. Everything is still there. The universe hasn't changed in the time we've been thinking about it. The black holes are exactly where they were. The gravitational waves are still rippling. Sagittarius A is still sitting at the center of the galaxy, 4 million solar masses of quiet, patient darkness, surrounded by its crown of orbiting stars. Let your body get a little heavier now. Let the numbers go. You don't need to hold on to them. Let the event horizons dissolve. Let the accretion disks cool. Let the gravitational waves pass through, and they are passing through, right now as you lie there. Ghostly ripples in the geometry of space moving through you and the Earth, and everything, without disturbing a single hair on your head. You are permeable to the universe's deepest signals. They pass through you constantly. You are more transparent to gravitational waves than glass is to light. And yet here you are, solid, warm, here. Somewhere in the universe right now, a star is dying, and another one is being born. Gas and dust and the remnants of ancient supernovae are condensing in a cold molecular cloud, pressure building, temperature rising, until the nuclear fires ignite and a new star blinks open for the first time. Small and fierce and orange, surrounded by a disk of gas and dust that will someday become planets, maybe oceans, maybe something looking up at the sky and wondering. And somewhere else, 2 black holes are spiraling toward each other with infinite patience, their gravitational wave emission growing stronger with each orbit. Each merger event 1 billion or 2 years away, billions of gravitational wave cycles from now, and the universe is counting them. This is what the universe is doing tonight. It is making and unmaking. It is patient. It is vast. It contains you in the way it contains everything, briefly, specifically, exactly as you are. Sleep well. The black holes will be here when you wake up. the Milky Way will still be turning, and you will still be here on the pale blue dot, circling a middle-aged star in the outer suburb of an ordinary galaxy, in the only corner of the universe that we know for certain is awake and watching.